Welcome to this tutorial. In this question, we have got a section based on electrochemical reactions, question 8. The question reads as follows. Learners want to identify an unknown metal X using a standard half cell, and this is the cell notation for the standard half cell. They set up an electrochemical cell under standard conditions using two half cells as shown in the diagram. We are given the diagram here. The initial EMF of the cell is 1,20. So the E standard for the cell is 1,20. State the standard conditions under which the cell functions. Now this is something that we just need to remember. It will be given in your notes. So for 8.1, we know that we have got the three conditions, standard conditions, which are temperature, and then also the other condition is pressure. If your substances are involving a gas, like here we've got a hydrogen that is being pumped, so pressure will apply. So pressure, and then the other one is the concentration. Concentration relates to the concentration of the electrolytes over here. So we have got the electrolyte with the hydrogen ions and another electrolyte with X2 plus ions. So with regards to temperature, we know that the standard or the standard condition under temperature is 25 degrees Celsius, or we can change that to Kelvin, which is 298 Kelvin. For pressure, we are looking at 1 atmosphere. What atmosphere is equivalent to 101.3 kilopascals. So you can write in one of these. And then concentration is 1 mole per cubic decimeter, the concentration of the electrolytes. Remember, these standard conditions are given in your data sheet, so you'll find them in your data sheet. And then we have here question 8.2. State one function of component Y. Component Y is a salt bridge. This is a salt bridge. Now the salt bridge, there are more functions to it, but you can list any one. They just want one. So one function of the salt bridge is to complete the circuit. It completes the circuit. If you want to list another one, just for study sake, we have got completing the circuit. The other function is it separates the electrolytes. So it separates the electrolytes so that they do not mix, of course. So that they do not mix. They do not mix. So you can give this as your answer or that one as the answer. The other function of a salt bridge is it also supplies the path through which the ions can move so as to ensure to restore neutrality. So you can say it restores neutrality. It restores neutrality. So any one statement here, you can be given a mark for the function of the salt bridge. Then we have got the question 8.3. Identify X by means of a suitable calculation. So here we were given that the metal X is unknown. So we need to identify what metal is that. Now, this statement reads, there's a statement given here that after the cell is operated for some time, it is found that the mass of electrode X has increased. That is very important to answer question 8.3 as well as question 8.4. So we know that in these two half cell, one half cell is the anode and the other one is the cathode. Now this statement will tell us which one is the anode and which one is the cathode. Now we know that the anode is the one where where oxidation is taking place. In other words, the substance will decrease, the electrode will decrease in mass. And the cathode is the one where gaining of electrons is happening. So we expect the electrode to gain the mass. So here, what they are telling us about electrode X is that electrode X is the cathode. So this is a cathode, and this is the anode. So the hydrogen is our anode, so this is undergoing oxidation. It is losing electrons, and this one is undergoing reduction. There is gaining of electrons on that side. That's why this electrode is increasing in mass. So now, to calculate this, we have to use the equation for the E standard for the cell. So 8.1, the equation for the E standard, or the standard cell potential, which is written, pronounced as E naught, E0, or E standard for the cell, is calculated as the E standard for the cathode minus the E standard for the anode. Or you can write it as the E standard for the reduction, and the E standard for the oxidation. Now this formula is also given in your data sheet, so you can refer to it if you have forgotten which one subtracts what. So now here we are given that the initial EMF of the cell is 1,20, so we know the E standard for the cell is 1,20, so we can substitute 1,20 volt will be equal to the E cathode is the X that we are looking for. So in this case, because we are told that X is increasing, so it means we are calculating the E cathode. So E standard for the cathode minus the E standard for the anode. Now our E standard for the anode is here on the anode side. We have got a hydrogen electrode. Now this hydrogen electrode is commonly referred to as the reference electrode, because its E standard is always referenced as a 0.01. So the E standard for this half cell is 0.0 volt. We can actually get that from the table of reduction potentials. Actually, that's what we must use here. So if you go to, I'm using, there are two tables. There is table 4a and table 4b. So I'm using table 4b. You'll be provided with these standard reduction potentials in your exam. So we'll find that the hydrogen, the reference electrode is given here, which is for the hydrogen. So its reference, its half cell potential is 0.0, which is 0 volt. Now, so we have to allocate the half E standard for the half cell on anode as 0 volt. So this is 0 volt. So this is 0. Now when we calculate the E cathode, so take the 0 to this one, is basically means that our E standard for the cathode is going to be a 1,20 volt. So we have to go back and check on our standard reduction potential, our tables, to see which substance or metal has got this value here. So we scroll back to our standard reduction potentials, look for positive 1,20, and the positive 1,20 is found over here. So this is the 1,20. So which means that this cathode is the one that is being referred to. So our cathode is a platinum cathode. So which means our metal is going to be platinum. So coming back to this, we can say therefore X is platinum, Pt. Means our metal is platinum. So that's how we can calculate that. And then 8.4, write down the oxidation half reaction that takes place in the cell. Remember, this is a redox reaction. There are two processes happening. There is oxidation and reduction. So there is loss of electrons and the gaining of electrons. So which one is losing here? The oxidation half reaction. The oxidation half reaction is the anode, which is the hydrogen half cell. So the hydrogen half cell is the oxidation. In this case, we write our equation from the right to the left. Okay, if we use what is called the big C, if we use the big C, the way we write a C, we start on our top right here, move to the left. So this is our oxidation. And then we go down to our reduction. The reduction, we write it from left to right. That is the gaining. So all equations on our table of reduction potentials, we write as right to left for oxidation. So we are going to write this equation 2H2 plus 2E, and this is a reversible reaction into H plus. So we write that as H plus. We are answering 8.4. So our answer 8.4 is hydrogen, which is our gas, being reduced. Use one arrow here, don't use two arrows, reversible. So hydrogen gas is losing electrons to give us H plus 2E. Okay, now because there are two, we have to have 2H plus. Just copy this one here, which is a 2H plus 2E, give you that. So that is our oxidation half reaction equation for the oxidation half reaction. And then we have the next section, which says the half cell X plus is now replaced by AU. This is gold. This is a half cell of gold. And then the initial EMF of the cell is now 1,50. As the cell operates, the AU electrode increases. So if the AU electrode increases, which means it is also a cathode. In other words, it is gaining. So arrange the oxidizing agents. So the oxidizing agents for the metal, which is platinum, the gold, and the hydrogen, in order of increasing strength. So here, remember, we are looking at the oxidizing agents. Fully explain the answer. Now, once more, we have to go back to our table of reduction, standard reduction potentials. Now we have this equation here, which is our hydrogen, where we get the H plus. Now remember, they want us to answer the question in terms of oxidizing agents. So you have to focus on the left side of the equation. Left side, there is a reversible sign, so we are looking at the left side, this hydrogen. So we've got a hydrogen H plus here, and here we identified our metal as a X plus, which is a PT2 plus. Now they are saying that when we replaced the platinum, the E standard for the cell changed from 1,20 to 1,50. So it means that it is somewhere here, somewhere there. That is where our Au3 plus is. Remember, the stronger the oxidizing agents become, the greater the EMF. In other words, the further away your half cells are, further away I mean we had a platinum here and a hydrogen. Now this gave us a 1,20. Now this one gave us a 1,50 volt. So we'll see that the EMF of the cell gave us a higher value. So it means that the Au3 plus is actually higher than the oxidizing agent, which is for Au3 plus. Remember, our oxidizing agents, we'll find them on the left side. So the Au3 plus for gold would be stronger than for that one for platinum, and platinum will be stronger than hydrogen. So what we have here is to answer the question. The question says arrange the oxidizing agents in order of increasing strength. So for 8,5, the weakest one will be hydrogen, followed by the X2 plus, which is our platinum, and then followed by the Au3 plus. Now, what reasons do we give here? They say fully explain the answer. So what we can give as the reason is that the cell, we find that when we used the Au3 plus, the EMF of the cell increased. So the cell containing Au has a higher EMF than the cell containing PT or X plus. Therefore, Au3 plus, these gold ions, Au3 plus is a stronger oxidizing agent than PT2 plus. Okay. That will explain the answer to that. Now, coming back, I just want to explain further here. We say that the cell containing Au has got a higher EMF than the cell containing platinum. Therefore, Au3 plus is a stronger oxidizing agent. Now, when you look at your standard reduction potentials, there are these arrows here. There is one arrow on the left, which is referring to strength, increasing strength of oxidizing agents, which means as we move from the top of the table on the left side of the equation, our oxidizing agents are increasing. Okay, so that's why we say that when we take the hydrogen, which we got here, and the platinum, which we had got, so it means the platinum is stronger than hydrogen. Now when we use the gold will be somewhere here, which is remember it was 1,50, so it's somewhere between 1,51 and 1,36. So it means when we use the gold, we got a greater EMF. So it means here we must have an Au3 plus, which itself is also greater than P2, platinum ions. So that's why we are saying that because we got a higher EMF, therefore it means that the Au3 plus is stronger because we are going further down. So Au3 plus is stronger than platinum ions. So that would explain the reason why we can arrange them in that particular order. So that completes the question, which has got 14 marks.